The second lesson in our reactions and stoichiometry unit is on balancing chemical equations. One learning target for this lesson, and that is simply to be able to balance chemical equations. Now, the question often comes up, what does it mean to balance an equation, or why do we have to balance the equation? The reason for that is the law of conservation of mass. What the law of conservation of mass tells us is that in any chemical reaction, the mass is neither created nor destroyed. Another way of looking at that means that the atoms that are in the reaction, they're either combined, they're separated, or they're rearranged, or a combination of those. And thus, a chemical equation should represent this. In other words, whatever atoms we start with on the reactant side, we have to end with on the product side. We can't lose any atoms as we go to the products. Likewise, we can't gain atoms going to the products. So consider this. Let's say we consider the formation of water from its component gases. This would be an equation for the reaction. We have hydrogen gas reacting with oxygen gas to form water. Well, if you take a look at that equation, you'll note that there are two oxygen atoms on the left side of the equation. Here are the two here, O2. And then there's only one on the right side with the H2O. So the question is, what happened to that second oxygen atom? According to the law of conservation of mass, it can't just disappear. It still has to be there. Well, it's actually there, but we have to show it by balancing the equation. So we might write it like this. We could show that we form two molecules of water by putting a coefficient 2 in the front of the formula for water. Now notice that would give us two oxygen atoms to match the two oxygen atoms that are on the left. But you might also notice now that we have four hydrogen atoms on the right, because I have two water molecules, each with two hydrogen atoms. So that would give us four atoms in total of hydrogen, but there's only two on the left. Well, we could counteract this by including two molecules of hydrogen gas on the left. So now notice there would be four hydrogen atoms on the left and four hydrogens on the right, two oxygens on the left, two oxygens on the right. The equation is balanced. In other words, what we're showing here is we're showing that we're starting with the same number of atoms that we finish with. Here's a picture to help you understand this. This is just a picture of exactly what this equation here is showing us. Notice we have two molecules of hydrogen. Each are H2 because remember it's diatomic. And then we have one molecule of oxygen, which is O2. And then we can see how those atoms are separated from each other and then combined in a different manner to give us two molecules of water. So notice there are the same number of hydrogen atoms on each side. There are the same number of oxygen atoms on each side. This is what we mean by balancing the equations. All right, so let's take a look at balancing equations. I have a few different examples here for us to look at. So I'm just simply saying balance each equation. I do not have a list of steps to give you as far as how to balance an equation. And the reason is there are so many different possibilities. The list of steps would be dozens, if not hundreds of steps long. The best way to do this is just to look at some examples. I will give you some hints or tricks along the way. But the only way to really get good at this is simply to practice a lot, to balance as many equations as you can, and it will not take you too long until you are quite adept at doing this. So let's take a look at this reaction here. We have magnesium reacting with hydrochloric acid, that would be the HCl, and then from that we get magnesium chloride, and we get hydrogen. So the first thing we want to do is we want to count the number of atoms of each element on either side or both sides of the equation. A good way to do that is to simply list the symbols for the elements that are in the reaction below the arrow. So notice we have magnesium, we have hydrogen, we have chlorine. And I'm simply going to look at the equation here and I'm going to count how many magnesium atoms are on the left, how many are on the right. Same thing for hydrogen, same thing for chlorine. So on the left side, I can see there is one magnesium atom. On the right side, there's also one. On the left, there's one hydrogen atom. On the right, there are two. I can tell because of the subscript 2 here next to the H. On the left, there is one chlorine atom. On the right, there are two. Again, the subscript 2 indicates that for us. What we need to do now is we need to change the coefficients that are in front of the symbols or the formulas in order to balance the equation. Now I say change the coefficients because at this point the coefficient in front of all these is 1. Now remember from math class, that's understood. If there's no number, there's no coefficient listed, it's understood to be 1. So right now we're showing 1 atom of magnesium reacting with 1 molecule of hydrogen chloride or hydrochloric acid to give us 1 molecule of magnesium chloride and 1 molecule of hydrogen. But I can see from my count here, the reaction, the equation is not balanced. I do not have the same number of hydrogens on either side, nor chlorines. So ask yourself, how many atoms of hydrogen would I want to get on the left side? Well, is there a way I could get there to be 2 atoms so I could match what's on the right? The answer to that is yes. If I come up here and I write the coefficient 2 in front of the HCl to have 2 molecules of the hydrogen chloride, that would give me 2 atoms of hydrogen. And then as I do that, I want to update my counts for each addition of a coefficient. So from doing this, I can see on the left side, I now have 2 atoms of hydrogen. And then notice we also changed the chlorine atoms. This coefficient does not just go with the hydrogen. This says we have 2 molecules of this entire thing. So that would give us also 2 atoms of chlorine. Now if we take a look at our counts, we'll notice the equation is balanced. We have 1 magnesium atom on each side, 2 hydrogen atoms, 2 chlorine atoms. It is balanced. We've done the problem. One thing to note, in no way can we ever change the formulas in the equation. Why not, you might ask? Well, consider this. Maybe you looked at this and said, well, I see there were 2 chlorine atoms here on the right. Why couldn't I just put a subscript 2 here next to the chlorine to give me 2 on the left? Well, the reason for that is the formula for hydrogen chloride or hydrochloric acid is HCl. It's not HCl2. By changing the subscripts in any way or adding subscripts, you are changing the identity of the substances, which would not be what we need to do. All right, let's take a look at another one. So notice here we have copper reacting with silver nitrate to give us copper nitrate. That would actually be copper 2 nitrate and silver. So we want to list the things we want to balance. And to note here, notice at the bottom here, I have not listed nitrogen and oxygen separately. I've just listed the polyatomic ion. This is a little bit of a shortcut that could help you. Whenever it's possible, you want to balance the polyatomic ions as one unit. Now, I say whenever it's possible, and here it is possible, and the reason is, you'll notice that nitrate, the NO3 ion, appears on both sides of the equation, and then there's no nitrogen or oxygen anywhere else. So what that means is I can balance that as one whole unit, or I can think of it as one atom. This simply makes my counting a lot easier. So when I count this up, there's 1 copper atom on the left, there's 1 copper atom on the right, there's 1 silver atom on the left, there's 1 on the right, there is 1 nitrate ion. Again, I'm counting this whole thing as one unit. There's 1 nitrate ion on the left, and there are 2 nitrate ions. Notice the subscript there with the parentheses. There are 2 nitrate ions on the right. Now I need to add coefficients. Well, to start with, the only thing that's out of balance is the nitrate ion. Can I get 2 nitrate ions on the left? And the answer to that is yes. If I have 2 of those particles, actually that would be a formula unit is what that would be. That would give me 2 nitrate ions. Also notice that would give me 2 silver atoms as well. Well, if I have 2 silver atoms on the left, I would need there to be 2 silver atoms on the right. So we can put a coefficient 2 in front of the silver on the right, and that would give us 2 atoms of silver, and the equation is balanced. All right, here's an example that's a little more complex than what we've seen. We have 3 elements here. We have carbon, hydrogen, and oxygen. And if we count this up, you might see why it's a little more complex. We have 2 carbons on the left. See here from the C2H6. There would be 1 on the right in the CO2. There are 6 hydrogens on the left, and there are 2 on the right. On the left, we have 2 oxygen atoms. You can see those here. And then on the right, there are 3 oxygen atoms. This is the first time we've seen this. Notice oxygen appears in both the products. A common mistake here would simply be to see the CO2 and list this as 2 oxygen atoms, but notice we also have an oxygen atom in our water molecule as well. So that makes this a little more complex. Another reason this is a little more complex, notice every one of these elements is out of balance to start with. In the previous two examples, it was pretty apparent how we wanted to attack balancing the equation because there was only one or two of the elements that were not balanced. So you might ask the question, well, which one do I start with? Which element do I want to balance first? Here's a good hint. You want to save any lone elements for last. What I mean by that is this. When I look at the equation, I notice that oxygen is by itself on the left side. So that makes it a lone element. I'm going to save that one to balance for last. The reason is, if I have the carbon and the hydrogen balanced, then I can go back and I can add a coefficient in front of the O2 and only change the O2. I don't have to worry about putting a coefficient there and then changing one of the other elements I already have balanced. So let's balance the carbon and hydrogen first. So to balance the carbon, I need to get there to be 2 carbon atoms on the right. So I'm going to put a 2 coefficient in front of my carbon dioxide. That gives us 2 atoms of carbon. Notice it also changes the oxygens. We now have 5 oxygen atoms on the right. Again, don't forget my oxygen in the water here. So there's 1 there plus the 4 that I have now in the CO2. That gives us 5. To balance the hydrogen, we would need 3 molecules of water. 3 times 2 would give us 6 hydrogens. And again, notice that changes the oxygens. We now have 7 oxygen atoms on the right, where I have the 4 here in the carbon dioxide plus the 3 from the water to make 7. All right, so now we have the carbon and the hydrogen balance. The only thing left is oxygen. That's what we kind of set out to do here. So ask yourself, what coefficient would I put here in order to balance this? Well, when it's useful or helpful, as it is in this case, don't be afraid to use a fraction to balance it, at least initially. The reason I say that is I know I need 7 oxygen atoms on the left side because I have 7 on the right side. And notice, no matter what coefficient I put here, I have to multiply it by 2 because I have O2. Well, that would make that coefficient 3.5 or 3.5 because 3.5 times 2 would be 7 oxygen. So the equation is balanced, just like this. One slight problem, though, is the convention for balancing equations is to only use whole numbers. So once we get it balanced with a fraction like we have here, we want to go through and multiply each of those coefficients by some number to make them all whole numbers. So we want to get rid of the fraction by multiplying each coefficient. This is very much like the same thing you do whenever you're writing empirical formulas. You get your mole-to-mole ratio. If you have a fraction, you need to multiply. Well, I look here, the only fraction I have is a 3.5 or 3.5. So I'm going to multiply every one of those coefficients by 2. So I'm just going to cross out the coefficients. And notice there we will then double all of them. So that gives us 2 molecules of the C2H6. That gives us 7 molecules of oxygen, 4 molecules of carbon dioxide, and 6 molecules of water. And the equation is balanced. If you wanted to, you could go through and double all of your atom counts here. It's really not necessary, though. Once we get it balanced, as long as we keep the coefficients in the same ratio, the equation will remain balanced. All right, you see basic ideas here and examples of balancing equations. The only way to get comfortable with this and to get good at it is to balance a lot of these. So I have a couple of practice problems here. Each of them might present a little bit of a different hint for you, but go ahead and look at the equation, pause the video, try to balance it yourself, and then look at my solution. First one, we have iron reacting with chlorine to give us iron 3 chloride. So here we have 2 elements, iron and chlorine. I can count up the number of atoms on each side. We have 1 atom of iron on the left, 1 on the right, 2 chlorines on the left, and 3 on the right. Here is a good case where we want to think about a least common multiple. The reason I mention that is I can see in order to balance the chlorines, no matter what coefficient I put in front of the chlorine on the left, I have to multiply it by 2 in order to get the number of atoms. On the right side, no matter what coefficient I put here in front of the iron chloride, I have to multiply it by 3. So whatever number of atoms I have has to be a multiple of both 2 and a multiple of 3. So what is the least common multiple of 2 and 3? Well, the answer to that is 6. So ask yourself, what coefficient do I need to put in front of the Cl2 to give me 6 chlorine atoms? Well, the answer to that would be 3. 3 times 2 would give us 6 chlorine atoms. And on the right, what coefficient do I need to put in front of the iron chloride to give us 6 chlorine atoms? The answer would be 2, because 2 times 3 would be 6. So that gives us 6 chlorines on the right. Don't forget, by putting the 2 coefficient in front of the iron chloride, we also change the number of iron atoms. There are now 2 on the right, so we need 2 on the left. So notice the coefficient 2 now on the left side, and that makes our equation balanced. One more example. Here we have a decomposition reaction. That's a term we'll be learning about in our next lesson, actually. It simply means we have one reactant breaking down to more than one product. At first, this looks quite complex, but once we start to look at the numbers, it's really not too bad. Here is an example where even though we have a polyatomic ion on the left side, notice we have the ammonium ion here, we can't balance that as one unit because the ammonium does not appear on the right side. So here we're just going to balance the individual elements, nitrogen, hydrogen, chromium, and oxygen. So when we count this up, I can see there are 2 nitrogens on the left. Remember your parentheses here, the 2 subscript applies to everything inside the parentheses, so that would be 2 nitrogens on the left. There are 2 on the right. We have 8 hydrogens on the left. Again, notice that would be 2 times 4 to give us 8. There are 2 on the right in the water. We have 2 chromiums on the left. We have 2 chromiums on the right. We have 7 oxygen atoms on the left. And then we have 4 on the right. Notice here, like we saw in the previous example, oxygen appears in more than one place. We have 1 oxygen atom in the water plus the 3 in the Cr2O3 for a total of 4. So if possible, we only want to add coefficients where necessary. That's kind of maybe a no-nonsense type of hint there. And what I mean by that is this. When I look at my atom count, the nitrogen is balanced to start with, as is the chromium. So if I can avoid it, I don't want to change those counts. I don't want to add a coefficient to any of those substances that would change the nitrogen or the chromium. Now, there are certainly some examples, we've already seen some, where that is not possible, where adding a coefficient will actually unbalance one of the atoms. In this case, actually, that is not the case. It is very helpful to think in terms of particles and molecules, and here's what I mean by that. When I look at my atom count, I can see I need more hydrogen and I need more oxygen on the right side. In fact, I need 6 more hydrogen atoms and I need 3 more oxygen atoms in order to balance this. Well, if I look at my substances on the right side here, I have one of the products, the water, that contains hydrogen and oxygen. And it contains hydrogen and oxygen in the same ratio that I need them. We said we needed 6 more hydrogen and 3 more oxygen. Well, that's a 2-to-1 ratio. Notice here we have 2 atoms of hydrogen, 1 atom of oxygen in a molecule of water. If I need 6 more hydrogen atoms, that means I need 3 more molecules of water. If I need 3 more oxygen atoms, I also need 3 more molecules of water. So I ask myself, how many would I have then? Well, right now there's 1 molecule. Remember that there's no coefficient there. It's understood to be 1. I need 3 more, so that's going to give us 4. If I count up my atoms now, that gives us 8 hydrogens on the right. 4 times 2 is 8. And that gives us 7 oxygens. Notice I have 4 oxygen atoms here in the water, plus the 3 from the Cr2O3 for a total of 7. The equation is balanced. In this lesson, you've seen several examples of balancing equations. Over the course of the next few days, we will practice this lots of times in class. It's the only way to get good at this, is to just balance as many equations as you can, and you will become much more comfortable because you start to see all the different scenarios that can possibly come up.